and Giacomo, both located at the Universidad de Valencia in Spain. So today I'm going to discuss the cosmological and astrophysical applications of a non-zero theta angle in QCD-like theories. So the outline of my talk comprises two main parts: an introduction, where I will discuss the SIMP scenario, strongly interacting massive particle scenario, and also the SIDM, self-interacting dark matter scenarios. And then I also going to discuss QCD-like theories, in particular, how the dark matter is realized in these theories. In the second part of my talk, I basically will discuss the effects of a non-zero theta vacuum, in particular the pion interactions, the new pion interactions generated from this theta term, and also the cosmological and astrophysical implications thanks to this theta term. And finally, I will conclude and present some view outlook of our work. So we have that the evidence that matter is abundant and compelling. We have evidence coming from different length scales. For example, a galactic scale such as the galactic rotation curves, at extragalactic scale such as the cluster and supernova data, bullet cluster, weak lensing, etc. And also at cosmological scales as the CMB anisotropies. All this evidence is telling us that the dark matter accounts for around 1/4 of the energy density of the universe. And if this dark matter is composed by particles, it means that there must be massive, neutral, and cosmological stable. So despite of this evidence, the nature of the dark matter is still unknown. We don't know, for example, what is the preferred parameter space of the dark matter for the dark matter. In particular, we have that the dark matter mass can vary along 40 order of magnitude, and also the scattering rates of the dark matter with the standard model particles can also vary, for example, 50 orders of magnitude. For sure, we do have a lot of dark matter candidates, for example, the WIMP, where the neutralino is the archetype of the weakly interacting massive particle paradigm. We also have the stellar neutrinos, axions, gravitinos, and also the SIMS, the strongly interacting massive particles. By far, the WIMP particles are the more well studied in the literature. However, kind of a scenario is not free of challenges. For example, we have that for example, for the simplest scenarios, as the singlet scalar dark matter scenario that is realized thanks to a C2 symmetry. The dark matter mass in these scenarios, must lie around the Higgs resonance or about the TB scale. So despite of being very appealing, this paradigm, this scenario is not free of challenges. And because of that, in the rest of my talk, I'm going to focus in this kind of paradigm scenario, the 3-to-2 SIMP paradigm. So this paradigm was proposed by Hochberg et al. In 2014. So here, the dark matter is the lightest particle in a nearly secluded dark sector, and the dark matter abundance is set by 3-to-2 or 4-to-2 number changing processes, in contrast with what happens in the WIMP paradigm, where the dark matter abundance is set by 2 going into 2 standard model particles. Here, these 3 to 2 and 4 to 2, etc. interactions only involve dark matter particles. So we have 3 dark matter particles in the initial state and 2 dark matter particles in the final state. So at the end, we have that the dark matter abundance is set by the number changing processes. And also notice that the mass, in order to reproduce the correct dark matter abundance, the dark matter mass must lie around 100 MeV. In comparison, what we have in the wind paradigm, where the dark matter mass must be around the electroweak scale. So these are the, we say, the main features. And in contrast, also with the wind paradigm, where the elastic scattering of dark matter particle is basically negligible, we have in this scenario, in the same scenario, that these elastic scatterings 2 to 2 are constrained by cluster observation. So usually in this kind of scenarios, this rate, the rate associated with this process is not negligible. So we have to take into account the observations coming from clusters. And a key point that must be ensured in this scenario, in this kind of scenarios, is that the thermal equilibrium between the standard model and the dark sector must be achieved in some way. For example, by introducing some specific portal. So typically, we assume that the dark sector and the visible sector, the standard model sector, are in thermal equilibrium. So they share the same temperature. The model building requirements are, in that case, I will say, model dependent. But these technicalities, in principle, do not affect the dark matter abundance. So that is the idea. On the other hand, we have also that the collisionless cold dark matter paradigm is not free of challenges. For instance, M-body simulations predict at smaller scales, so this scales less than 100 kiloparsec, predict universal halo profiles with large central density, in contrast to certain observations. For instance, here we display the dark matter profile as a function of the radius, and the simulations predict this behavior where for alpha is close to -1, and in comparison with the observations that prefer a flatter profile, meaning that alpha is nearly 0. This is the core versus Cox problem. And we also have the too big to fail problem, that where this simulation also predict very massive satellite halos in the Milky Way, which have not been observed. So for instance, these are the predicted curves from these M-body simulations. However, we only observe this kind of Milky Way satellites with masses that are not so high. For sure, these two problems can be maybe mitigated or resolved by introducing some baryonic feedback into the simulations. However, we would like to address these issues by considering the appealing alternative of collisionless CDM. And this scenario is what known today as self-interacting dark matter. That it was proposed by Specker and Steinhardt in the late 90s. So in this scenario, we have that it is possible to have dark matter elastic scatterings in the inner regions, so 2 to 2 processes. In such a way, the central density can be decreased up to be compatible with the simulations. So in order to achieve this, we require a strong self-interact dark matter scatterings in dwarfs. This is a key point to bear in mind. So the cross-section of the mass must be between 1 and 210 or even 50 centimeters squared per gram. For the matter velocities, between 10 to 200 kilometers per second. So this is the typical velocities in dwarfs. On the other hand, we have to be below, so this quantity must be below the cluster bound that impose that must be less than 0.5 centimeters squared per gram, however, at larger scales. So that means at large velocities of the order of 1,000 kilometers per second. So this is the typical velocity of dark matter particles in cluster, whereas this is the typical velocity of the matter particles in dwarfs. So in order to explain, to solve these small scale issues, we require this kind of values for sigma over the dark matter mass. So for sure, self-scattering cross-section that decreases with the dark matter velocity can lead to a better fit. So otherwise, if you have, for example, a constant, if this ratio is constant, so you cannot realize the SIDM scenario. Among the possibilities to realize the SIDM scenario, I will like to discuss the resonant SIDM, which was proposed by Chu, Garcia-Celi, and Murayama in 2018. This scenario, basically, in this scenario, basically we have that the matter scatterings are mediated by an on-shell resonance. And due to this resonance, we have that the cross-section receives an enhancement for the matter velocities near to BR. This BR is just an alternative parametrization of the mass splitting. Notice that BR is defined in terms of the mass of the resonance minus twice the mass of the dark matter mass. So basically, BR is corresponds to the mass splitting. So some parametrization of the mass splitting. And in this paper, the authors showed that it is possible to successfully account for the required interactions as long as this BR is between 10 to the minus 7 to 10 to the minus 2. So in other words, the mass of the resonance is quite similar to the twice of the dark matter mass. Good. So the other ingredient of our work concerns about QCD-like theories. So these kind of theories are based on a dark gauge group, could be a unitary group or orthogonal or asymplectic. So we are going only to consider the unitary group. So concretely, we are going to consider SUN NC, where NC is the number of charts and the dark colors. So we are assuming a dark gauge group, similar what we have in the standard model to the QCD gauge group, but with the number of colors as a free parameter. We have another ingredient is that we introduce NF flavor of Dirac quarks in the fundamental representation of the color group, dark color group. And with this, we can write down the Lagrangian of the theory, which is given by the kinetic term for the dark gauge bosons, so the dark gluons, the kinetic term for the dark quarks, and also the mass term for the dark quarks. I am going to use with any difference dark quarks, and also gluons and dark gluons, and also pions and dark pions. So basically, I will refer only to the dark sector. So here, the visible sector will not play a role at all. Good. So this mass matrix is assuming to be diagonal, and usually the quark masses are equal. So the quark mass spectrum is degenerate. As happened in the standard model, in the standard QCD sector, we have that for massless quark, this Lagrangian, so if we consider M to be 0, so this Lagrangian features a global symmetry that is the product of two SUN groups. And the same happens in the standard model QCD sector. So the other ingredient is that the dark strong interactions confine at some energy scale, lambda, in analogy again with the ordinary QCD. So we assume that this dark sector confines and giving rise to a fermion condensate, which in turn induces a chiral phase transition that spontaneously breaks this global symmetry. And at the end, we have as the remnant symmetry, the vectorial part of this product of symmetries. This is completely analogous to what happened in the ordinary QCD. The difference that we are not fixing the number of colors, neither the number of flavors. So this condensate leads us to NF squared minus 1 pseudo-Goldstone bosons, the pions, the dark pions, which are described by the chiral perturbation theory, allowing us to write down the corresponding Lagrangian, which contains the kinetic term for the pions, a mass term, but this mass term also induces interactions, as we will see later, and also this quintic interaction that is known as the Wess-Zumino-Witten term. So this is the Lagrangian for the dark pions. Here, F pi is the dark meson constant, which is related to the scale, the confinement scale given by this expression. So for the case where the quark masses are like NO, we have that the flavor symmetry is still good. So it is possible to rely in the paradigm of effective field theory. So we can do calculations. And for the case of degenerate quark masses, we have that all the pions, these NF squared minus 1 pions, have the same mass, which is given by the product of B0 and the quark mass. For the particular case of 3 colors and 3 flavors, we have that this pion field can be expressed in this way. And notice here that we are just using the same notation as the ordinary QCD, just the notation. In other words, the 8 pions that we see here, all of them are the same. But just we are denotate them as the charged pions, the charged kaons, the neutral kaons, and pi 3 and pi 8. But they are the same. So they are not electrically charged, etc. Neither we are introducing a dark U1 cage group. It's just the notation. Okay, so with these interactions, we now can address the dark matter abundance in these scenarios. So here the dark matter is a thermal relic in the form of pion, and the relic density is set by these 3-2 processes mediated by the originated from the Wess-Zumino-Witten term. The corresponding cross-section, thermal cross-section, turns to be the wave suppressed, so it's velocity suppressed. And for the case of NC equal to NF equal to 3, we have that it is possible to explain the dark matter abundance for pion masses around 100 MeV and pion constants around, again, 100 MeV. So we have that these pions can also undergo elastic scatterings, 2-to-2 scatterings. In this case, however, the corresponding cross-section doesn't depend on the velocity. So in other words, in the ordinary QCD-like theories, it's not possible to realize the SIDM scenario. So it is possible to address the small scale issues that we were discussing above. Concerning the variable parameter space, here we display the pion constant as a function of the pion mass. The red line corresponds to the perturbativity limit. So this means that below this line, so the red region is within the non-perturbativity region. So our calculations are not reliable. So basically we neglect this zone. The blue region, so this blue line corresponds to the upper limit imposed by the observations on clusters. So this means that this blue region is ruled out by the cluster observations. The black points represent or correspond to the points that can explain all the dark matter abundance measured by Planck. And so at the end, as you can see, this scenario is basically borderline excluded because the allowed that the viable region compatible with this measurement is in tension with the cluster observations. So as a summary, ordinary QCD-like theories are borderline excluded due to the bullet cluster observations. And furthermore, they cannot realize the self-interacting dark matter scenario. Any question up to this point?
Oscar, what about constraint from spin-independent cross-section?
So this under this kind of scenarios, in principle, we are not the dark matter do not interact with the standard model, so you don't have a spin independent. However, in order to thermalize the dark sector with the standard model sector, you need to introduce a portal. So basically, at the end, the dark matter has to, in some sense, interact with the standard model sector. However, the analysis of, so this has been done in the literature, and the results remain in other words, so in order to address the constraints coming from spin-independent elastic scattering, so from data detection experiments, you need to introduce a specific portal. So that turns out to be model dependent. Okay, so up to this point is model independent.
I see. Thank you, Oscar.
Thank you for your question, Antonio. So now let's address the impact of having a non-zero theta term in these QCD-like theories. So now we are going to consider the same scenario, but with a non-zero theta term, however, small enough in order to make a perturbative expansion on theta. We will see how small must be this theta parameter. So thanks to the chiral anomaly, we can perform some chiral transformations in such a way this theta term can be moved from this theta parameter can be moved from this term to the mass to the mass term by, for example, choosing the trace of the charges of the pions equal to 1. So it is possible to move the theta parameter from this term to this term, and this is what we are going to do. So basically, the effect of the presence of theta appears in the mass matrix. So with this in mind, we have that the pion interactions get modified to this new Lagrangian, by this new Lagrangian. Basically, the kinetic term and the Wess-Zumino-Witten term remain equal. And due to this theta term, this theta parameter, non-zero theta parameter, we have that this term gives rise to interactions with an odd number of mesons and proportional to the theta parameter, to 1 power of the theta parameter. And notice that these new interactions are involved, for example, 3 pion fields. So this is a new cubic interaction. It's not present in the ordinary QCD-like theories. And we have also an extra quintic interaction. These interactions are controlled by these group factors that depends on the structure constant, etc. And this cubic interaction, in principle, may induce the decay of some mesons. So this is a completely new effect that is not present in the ordinary QCD theories. On the other hand, we have that this extra quintic interaction, notice that doesn't depend on some derivatives. So at the end, the 3-to-2 annihilations features a thermal cross-section that is not velocity suppressed. So is S-wave suppressed in comparison with the one coming from this term that is D-wave suppressed. So that is a remarkable difference between these two processes. And we have also that the masses of the pions are corrected by theta squared terms. So this means, as we are considering theta to be much more smaller than 1, we expect that the meson spectrum is quite degenerate. So the appearance of resonance are quite plausible. So we can expect easily resonance in our spectrum, in this meson spectrum. On the other hand, dark baryons and blue balls, dark baryons will be the dark proton, dark neutron, etc. Have typical masses of the order of lambda. So this justifies the assumption that the dark matter is made of the lightest dark meson. Okay, so what we are seeing is that the dark matter abundance is set just for by this meson. This process is involving only mesons, not the dark baryons, neither the blue balls. Good. So in order to illustrate the effect of a non-zero theta term, we define 2 benchmark models. The first one, for the Wisman, the first one, we set NC equal to NF equal to 3 with this quark mass hierarchy. And we are going to use the same notation as ordinary QCD. So we have 3 quarks, 3 dark quarks, and we will have 8 pions, in particular 1 eta, 4 kaons, and 3 pions. We are since we want to realize the SIDM scenario, we are going to focus in this in the parameter region where BR is less than 0.1. Under this condition, we have that the ratio of the meson masses are determined just by the quark mass ratio RUD. RUD is defined as mu over md. So notice that basically the mass of the eta meson becomes twice of the pion, the neutral pion. And also notice that the charged pions are basically degenerate with the neutral pion, and the mass splitting is controlled by this delta parameter, which varies from 0.8, 0.08 from 10 to the minus 5 for RUD from 0 to almost 1. So this is the mass spectrum of this benchmark model. We have the eta, the pion. So the eta is the heaviest meson, whereas the neutral pion is the lightest meson. And in between, we have the neutral kaons, the charged kaons, and the charged pions. Good. And also in this benchmark model, we have that eta acts as an unstable resonance. So eta can only decay into a couple of neutral pions. The decay into charged pions and kaons is forbidden. And neglecting theta squared corrections, we have that the masses of these mesons, the charged pions, etc., are given by these expressions in terms of the dark mass of the quark masses. Good. So this is the benchmark model 1. The benchmark model 2, we fix the number of flavors equal to small n plus 1, where n is larger than 3, larger or equal than 3, and choose the quark masses, the mass matrix as in this way. This means that we are considering small n flavors with the same mass n and just one heavy quark with a mass mu, such as we have this mass hierarchy. So again, we have a set of several dark quarks with the same mass m and a heavy dark quark with a mass mu. So due to this structure, we have that the SUNF symmetry breaks into a SU small n symmetry, where the NF square mesons organize as pions belonging to the adjoint of this SUN, kaons in the fundamental and anti-fundamental representations, and just one single eta resonance, where the masses are fixed by these mass parameters. For the case where NF is equal to 4, so 4 flavors, we have, for 4 flavors, we have again, we have 15 mesons that are divided into 8 pions, 6 kaons, 3 in the fundamental and 3 in the anti-fundamental representations, and 1 resonance. And notice that for small eta, BR is proportional to theta. So this means that for small thetas, for small values of the theta parameter, it is possible to have a small BR. And let's recall that BR controls the mass splitting between the lightest pion, the dark matter particle, and the eta resonance. So naturally, it is possible to have BR values for BR less than 1. In this scenario, again, eta is an unstable resonance, but just decaying into the pions, not to the kaons. Okay, so this is the consequence for this benchmark model. So now we are going to in this 10 minutes, the next 10 minutes, I will discuss the cosmological implications and astrophysical implications of these two, for these two benchmark models. So basically, we have that the presence of this theta 10 impacts the dark matter production due to the appearance of new number changing processes, such as the 3-2 annihilation, and also the decays and inverse decays, for instance, dark matter going into eta. For both scenarios, we have that all the stable mesons eventually convert into dark matter, as happens, for example, in the co-annihilating dark matter scenario. That is the typical behavior. We are going to refer the dark matter and his co-annihilating partners as pion dark matter. So this means that for the benchmark model 1, the dark matter is composed by the neutral pion and the charged pions. Whereas for the benchmark model 2, the dark matter is only composed by pions, not by kaons, neither the eta resonance for sure, because it's unstable. And again, bear in mind that we are assuming that the kinetic equilibrium is achieved between the two sectors. We are just we are agnostic about this, how this is achieved, but for sure the model building requirements for this are similar to those of the ordinary scenes. Concretely, you can introduce, for example, a hidden photon portal, an action light portal, or even vector resonance, etc. So all these kind of portals can be also taken into account at the moment of thermalize both sectors. So, but the implications of introducing this one or other portal are model dependent. So this is part of the work in progress that we are doing now. So now, due to this eta resonance, we have that eta behaves as a catalyzer. So this means that eta induces number changing processes such as 2-2, but notice that this 2-2 process involves an eta and one pion, one dark matter particle in the initial state, and in the final state, just two dark matter particles. So in this case, the number density of the dark matter particles increase or decrease by 1 unit. And the same for these decays and inverse decays. For BR less than 0.1 and theta larger than 10 to the minus 4, we have that these decays and inverse decays are both active even after all the number changing process have frozen out. This means that they are still active even the other process have frozen out. So with this in mind, and lying in this region of the parameter space, we have that the dark matter abundance is set by not the 3-2 ordinary process, but the resonant 3-2 process. And this 3-2 process is displayed in this figure, where this eta is an unshed resonance. So basically, we have a 2-to-1 process, and then this eta interacts with this pion going into 2 pions. So at the end, this 3-to-2 pions is mediated by an unshed eta resonance. This process leads us to a set of coupled Boltzmann equations, and that we can solve numerically. And in particular, for example, here we display the yields for the dark matter particles for a specific point of the parameter space. The yield as a function of Z, that is the mass of the neutral pion over the temperature. And notice here that the yellow line and the black line corresponds to the yield of the neutral pion and the charged pions. Notice that at the moment of freeze out, both pions, the neutral and the charged pions, contribute to the dark matter abundance. However, after some time, the charged pions annihilate to each other into the neutral pions. So the charged pions are converted into the neutral ones. So basically, at the end, the dark matter is composed by just neutral pions. And notice also that the yield of the eta meson is basically negligible. So taking into account this result, we can simplify the set of Boltzmann equations to one single Boltzmann equation that is controlled by this thermal cross-section that is associated with this process to a 2-2 process, where in the initial state we have an eta and a pion, and in the final state we have a pion, 2 pions. And it's independent of theta, and it's also the corresponding cross-section is S-wave supreme, so it's not velocity supreme. So that is a very interesting result. So now we display the viable parameter space compatible with all the constraints for the benchmark model 1. The dark gray region, this region is excluded by perturbativity, so the calculations are not reliable. This light gray zone give us our abundance. So the dark matter is overabundant in this zone, so it's also excluded. And this blue region is excluded by the bullet cluster observations. So at the end, the white space is compatible with all the constraints, and the dark matter abundance is reproduced along the plane for different values of RUD. This line corresponds for RUD equals 0, this for RUD equal 1/3, RUD equal 2/3, etc. So it is possible to be compatible with all the constraints thanks to the presence of the theta term or a non-zero theta term. This star corresponds to a benchmark point where we are going to address the astrophysical implications. Before that, let's discuss the cosmological implications for the benchmark model 2. So at the end, as I said before, basically the dark matter is just composed by pions. We have that the kaons are heavy enough in such a way they relic yield, that the relic abundance is negligible. And again, the relic density is set by this kind of process, 2-2 process. However, due to the large number of degenerate pions, let's remember that for the case of the number of flavor equal to 4, we have 15 mesons and 8 pions. So we have 8 degenerate pions. So due to this fact, the dark matter is reproduced in parameter regions in tension with the cluster bound. So we have that as long as the representation of the dark matter is large enough, the relic density is in tension with the cluster observations. So in other words, this suggests that the dark matter must lie in a small representation, which can be done breaking, for example, the mass degeneracy as we did for the benchmark model 1. And this is a generic feature of other color and flavor groups. Good. So benchmark model 2 doesn't work but we know how to make it to work. Finally, the astrophysical implications for this benchmark model, one in particular for this benchmark point. So we have that the dark matter particles, the pions, can also elastic scatter by the exchange of this eta resonance. So this means that it's possible to realize the SIDM scenario. And here in this plot, we display the velocity average cross section as a function of for different scales as a function of the velocity. Let's recall that small velocities between 10 to 200 corresponds to the velocities of the matter particles in dwarfs, so small scales, and velocities of the order of 1,000 or 2,000 kilometers per second correspond to large scale. So the dark matter particles lying in clusters. So notice that for VR of the order of 100 kilometers per second, that corresponds to in natural units of 3 times 10 to the minus 4, which again can be easily explained by this proportionality between VR and theta. Notice that it's possible to have a smaller scales, larger cross rates over the mass, larger values for the cross section over the mass, and at the same time be below this line. This line corresponds to the Baller cluster upper bound. So it is possible to be compatible with this bound large scales. So with this, we illustrate that it's possible to realize the SIDM, and so we can successfully account for the required interactions in a small scale helioms while avoiding the cluster constraints. So, it is possible to solve the small scale issues in the collisionless cold dark matter paradigm within this kind of framework. QCD-like theories plus a non-zero theta term. So finally, I will give you a brief summary. So we have pointed out a production mechanism for dark matter in QCD-like theories where the theta angle is not zero. So this requires a resonance mediating inverse decays followed by 2-to-2 process with a mass such as VR is less than 0.1. Let's remember that VR controls the mass splitting between the eta and the dark matter mass. The viable parameter regions can be compatible with the cluster observations on dark matter set scattering for theta values larger than 10 to the minus 4. That is okay, is small, but not too much small. And finally, the theta induced scatterings may address the apparent small scale anomalies of the collisionless cold dark matter paradigm. That is completely new feature of this scenario. The ordinary QCD-like scenario, even with non-degenerate quarks, are not they are not able to realize the SIDM scenario. And finally, we have that we just focus in unitary groups, but these are generic features of QCD-like theories based on orthogonal and also symplectic groups. Now, these are the summary and regarding the outlook. So this is work in progress. There are a lot of things that are to be done. For instance, in particular, considering the orthogonal and unitary groups. That is, in principle, is a easy task. The next goal is to address thermalization between the visible and dark sectors. So again, this can be done through the introduction on a hidden dark matter, action-like particles, and vector resonance, etc. These two remarks are in some way speculative, but it will be good to see what happened in what respects to the emission of gravitational waves due to this chiral phase transition in the dark sector. There are some studies that have been done for theta equals 0, but not for theta different from 0. And finally, since we have a new source of CP violations, it will be good to look for the implications for the matter-antimatter asymmetry. So how to bring this CP violation in the dark sector into the visible sector. That there are some studies that have been done using the same argument, but not within this framework. So that's all. Thanks for your attention. I will be happy to discuss about this with you. Thanks.
Thank you very much, Oscar, for the very nice and very complete seminar. Question from the audience? Any question from the audience? Oscar, question regarding this, the other possibility of using, for example, orthogonal or symplectic group in the analysis. You expect, for example, some advantage with larger group, or your expectation are that it may be, for example, reduce, let's say, particle content, or the feature will be more or less generic in both scenarios.
Okay, thank you, Antonio, for the question. Indeed, for symplectic groups, there is an advantage because the number of flavors can be two instead of three. So yes, there are some special features for each group, but in what respect to these general conclusions, I will say that all of them remain for all the unitary, orthogonal, and symplectic groups. And one thing that must be taken into account is that, for instance, if you have orthogonal, or if you are using orthogonal or symplectic groups, the portal in some sense is a bit different because the interactions must be different. Because, for instance, for the symplectic groups, you will have wild fermions. So, in other words, Majorana fermions, they will form Majorana fermions instead Dirac fermions. So there are some particularities associated with each portal.
So in principle, the constraint, for example, from this spin-independent cross-section, for some, they will provide different prediction. For example, will be different, yes. And some will be closer to the sensitivity than in other scenarios.
Yes. So I would say that the David detection constraints is not so strong. Instead, for instance, you have to take care that the new interactions are not so fast, are not so relevant, because otherwise you can spoil the prediction of you can spoil the 3-to-2 mechanism, because at the end, if these interactions with the visible sector are sufficiently high, sufficiently strong, so at the end you will have a wind paradigm. Okay, you will have the wind mechanism instead of the sim mechanism. So you have to take care that these interactions are under control, but at the same time that the interactions are high enough in order to thermalize both sectors, and also that the dark matter particle doesn't decay, or if decay, if the dark matter decays, so you have to guarantee that the lifetime is larger than the age of the universe. So all these constraints has been taken into account for the ordinary QCD-like theories, and have led to successful realization, successful models. Okay, so we expect that with a non-zero theta 10, the same conclusions remain qualitatively speaking. Okay.
Yeah. Thank you very much, Oscar.
Thanks, Antonio, for the question.
More questions from the audience? It seems that there are no more questions. So we thank Oscar for the very nice and very complete seminar. Thank you very much, Oscar, for the very nice seminar.
Thank you, Antonio. Thanks to the audience for listening.
And we meet on the next seminar.
Okay.
And we meet Oscar the Friday to discuss about the referee. So have a nice time, all of you. Thank you so much, Oscar.
Okay. Thank you.
Bye.